So we're going to do a few examples using the Bohr model that has energy levels. Now here we're given a lithium atom's energy levels up to n equaling 4. Now you can imagine these energy levels surrounding the atom. So let's say we have our lithium atom here, and then we have our ground state, which is n equaling 1, and then we have n equaling 2, n equaling 3, and finally n equaling 4. Now, you have electrons that live, in terms of the Bohr model, on these states, okay? But they can only exist on these energy levels. They can't exist in the middle, okay? So that's impossible in this theory. And what occurs is they can jump between states, but they have to have the exact amount of energy either being lost or absorbed in the form of photons. So in order for, this is n equaling 1, n equaling 2, n equaling 3, and n equaling 4. Let's say we have an electron on ground state of n equaling 1. Let's say we want it to jump and go to n equaling 3. In order for that to happen, our electron has to gain energy. We can think of it trying to climb a ladder. In order for that to happen, a photon has to come in with that exact amount of energy. That's the difference between n equaling 1 and n equaling 3, and it will be absorbed, allowing our electron to become excited and jump into our third energy level. Now, you're going to start to realize we're going to use this equation of our E photon equaling our final state of our electron minus our initial state of our electron. Something that often confuses people is based on the fact that sometimes your energy of your photon is negative, which hopefully you understand is kind of impossible. It doesn't totally make sense that the energy of a photon is negative, but it all depends on the perspective of what you're talking about. Okay, we're talking about it in the perspective of the atom. Okay, that's what this equation is. It's in perspective of the atom. So if an atom is absorbed, if a photon is absorbed, your atom is gaining energy, so it's going to be positive. So this is when something's absorbed. Okay, so your atom is gaining energy, so it's going to be a positive energy added into the system, and your system being the atom itself. If something is emitted, so that occurs when you jump from a higher energy level to a lower energy level. So say we have an electron existing in the fourth energy state, so up here. If it jumps down to the energy state of n equaling 1, a photon will be emitted. And this is going to be a negative energy in terms of your atom. Okay, it lost that energy of that photon. So if you have a negative photon's energy, that means it has been emitted. Now recognize that's not something you really need to memorize. It's just something useful to understand of kind of why we're getting negative values for a photon energy. Because at the end of the day, that doesn't totally make sense, right? You can't really have negative energies unless something's being lost. That energy isn't being lost, it's being emitted into the universe, but it's being lost in the perspective of the atom. So let's do a few examples here. How could an electron jump from ground state to the third energy level? So our ground state is n equaling 1. So we start here and we jump up to our energy state of 3. So we're going to use our equation, the energy of the photon equals the final energy level of the electron minus the initial energy of the electron. In this case, for us to increase an energy level, a photon is going to have to come in and be absorbed. Remember, in terms of your atom, in the perspective of your atom, it has gained energy. So we are going to get a positive outcome. So we can now go forward and understand that the final energy level of our electron is when the electron's in the third energy state. So E equaling 3, which equals negative 1.7 electron volts. The initial energy level of our electron was when it was in the ground state, N equaling 1. That energy state is negative 5.1 electron volts. So we can now plug these values into our equation. We can plug in negative 1.7 electron volts and subtract negative 5.1 electron volts. And from there, two negatives make a positive, and we will get 3.4 electron volts for our photon that is being absorbed. Now, we could go further and determine even the frequency of this thing and possibly what type of light or EMR this is. So remember, the energy of a photon equals Planck's constant times the frequency. So we could determine our frequency here really easily by taking the energy of our photon and dividing it by Planck's constant. Now, this is 3.4 electron volts, so we have to use Planck's constant. That is in terms of electron volts. So that would be 4.14 times 10 to the negative 15 electron volts times seconds. And that will give us 8.21 times 10 to the 14 hertz. If you went into your emission spectrum, you'll notice this sits around the UV light. Okay, so this would give off an absorption spectrum to jump there, and it would show the UV light blacked out, okay, that area, because again, it's being absorbed. Now, where do we go from here? Let's go to number 2. What frequency of photon would be emitted if an electron moved from the third energy level to the second energy level? So now we are going from our third energy level to our second energy level. We are lowering in energy levels, and in order for that to happen, we need to emit a photon. So the fact that we're emitting a photon, and that photon's energy is going to be exactly equal to the difference between these energy states. So if we use this equation, we have to be careful in understanding what's occurring. Okay. The fact that our electron is dropping energy states means our photon is going to be being emitted. And since it's being emitted, it's going to be negative. So what I'm going to have to do here is apply a negative to my photon, because again, I need to cancel that out. I need to cancel out the fact that our outcome is negative, because we can't have a negative photon energy. Okay, so this is because it's being emitted. Now, we already know that we start off at the energy level of 3. So the energy level of our electron initially is E equaling 3, which is negative 1.7 electron volts. The final energy level of our electron is the energy level at 2, which is negative 3.6 electron volts. So now I can plug these into my value or into my equations and start solving for the photon's energy. So this becomes the final energy state, which is the energy state of 2, minus the initial energy state, which was the energy state at the third energy level. And then from here, we can plug in our values of negative 3.6 electron volts minus negative 1.7 electron volts. Now, two negatives make a positive. So this is negative 3.6 electron volts plus 1.7 electron volts. Now recognize, good thing we brought along our negative value since we knew it was being emitted, because we get an outcome here that is a negative 1.9 electron volts. Okay, and again, the reason we're getting that is because this equation is in the perspective of our atom. Okay, so remember, we have our atom here, and let's just draw our two states, or our three states, I guess. We have our ground level n equaling 1, n equaling 2, and n equaling 3. We started here, and in order for our electron to jump down to energy level 2, our photon had to be emitted. Our atom lost energy. It lost energy. This is why we get that negative value, and this is why we apply the negative value here, because we can't have a negative photon energy. So now, in order to finally solve for our photon's energy, we will divide by negative 1 by both sides. So the photon's energy here is positive 1.9 electron volts. And again, it was emitted. And from here, we can solve for the frequency at which this photon was being emitted. So the energy of a photon equals h times f, so Planck's constant times the frequency. So our frequency equals the energy of our photon divided by Planck's constant, so 1.9 electron volts divided by 4.14 times 10 to the negative 15 electron volts times seconds, and that will give us an outcome of 4.58 times 10 to the 14 hertz. Okay, so in this case, we have a lower frequency than our original one, which makes sense because we didn't jump as big of a jump in this case. Since we have a lower frequency, it'll be a less dangerous EMR, and this actually falls in kind of the blue area. So this would be forming a emission spectrum. We would see blue light occurring in our emission spectrum. Furthermore, you could technically calculate the wavelength of this photon that's being emitted by simply using our relationship of C equaling the frequency times the wavelength. And C in this case is 3 times 10 to the 8 meters per second. Okay, so just recognize you could find the wavelength. Let's do one more question. Okay. What frequency of photon is required to ionize an electron at ground state? So probably since Science 10, you understand what ionization means. Ionization means your atom loses an electron. Electrons are being emitted from something. In order for an atom to lose an electron, it has to essentially be given enough energy due to an EMR, photon, to ionize. Now it depends on what energy level we're at, but we're going to assume it's at ground state. So in order for this electron to jump out and be released from the atom, a photon has to come in that equals that energy level's energy. So in this case, the energy of the photon that's absorbed has to equal the ground state's energy in order for this electron to be released by the atom. So from here, the energy of our photon has to equal 5.1 electron volts. You can determine its frequency again. by our equation, energy of a photon equals h times frequency. So in this case, the frequency equals 5.1 electron volts divided by that 4.14 times 10 to the negative 15 electron volts times seconds. And that will give us an outcome of 1.23 times 10 to the 15 hertz. Now recognize that's a bigger frequency than our other two solutions we got. We got times 10 to the 14 hertz. Down here we got times 10 to the 14 hertz. And this is now times 10 to the 15 hertz. This light, this type of EMR, is a stronger form of UV. And this, if we just were dealing with these energy states, this would be the highest frequency at which any type of photon could be emitted by this lithium atom. So I hope that was helpful to you all. And if you have any questions, comment down below or ask your teacher. And other than that, have a good day.